Hi, welcome to Math to the Power of Science. Today we'll be talking about sound. Sound is made when something pushes back and forth on the air. When the air is pushed together, it's called a compression, and when the air is spaced away, it's called a rarefaction. The frequency of the wave is how many rarefactions and compressions there are in a second. The frequency determines how high or low the sound is. The higher the frequency, the higher the sound. And as the frequency goes up, the wavelength, the distance between two rarefactions or two compressions, decreases. You've probably seen sound represented by this wave, but what does it mean? Well, this is actually a graph of pressure difference over time. The higher points are the compressions and the lower points are the rarefactions. The difference between average pressure and the highest pressure or lowest pressure is the amplitude, and that determines how loud or soft the sound is. The bigger the amplitude, the louder the sound. When a sound wave reaches our ears, it hits our eardrum, which then pushes some bones into the cochlea, which is a fluid-filled membrane, which sends a neurological signal to your brain, and which perceives it as sound. If you want to learn more about why a piano's C is different from a guitar's C, check out Vihardt's video that I'm putting in the description. So now we know a basis of sound, but how fast does sound travel? Sound isn't constant. It actually has an equation that you can use for ideal gases. The equation is based off the adiabatic constant, which is different for each gas, R, the gas constant. A gas is a molecular mass and its temperature. If you know all the constants of dry air, you can simplify this equation for dry air to 20.05 times the square root of the temperature in Kelvin. In 289 degree Kelvin air, or 16 degree Celsius or 60 degree Fahrenheit, sound will travel at about 340 meters per second. Now say in that same air you're traveling at 341 meters per second. You will start to travel in front of the waves you create, and this will lead to a buildup of sound, which is a shock wave that we call a sonic boom. Another type of shock wave is from an explosion. The blast pushes the air into one huge compression. The wave graph doesn't look like a regular sound though. It has a different shape. This is because when the blast goes off, it clears it into a near vacuum, which then air around it starts to trickle in, forming a less noticeable rarefaction. Thanks for watching. Leave a comment down below with suggested topic for a future video. If you like what you saw, please subscribe.